quiz. Here, lab quiz. I think that's due on Friday. Don't forget about that. Today at noon, we have a research talk by our botany candidate. His teaching demo was yesterday, 9:30. Anyone go? Apparently, it's pretty decent. Pretty cool. So, in talking to him, it seems like his approach to teaching the botany would be similar to kind of how we approach the parasitology course. Instead of just straight memorization, actually kind of talk about some of the adaptations and some of those neat things that plants have, so that you can associate some of the names with some of their traits. So seems interesting. Can't wait to hear them. So yeah, that's at noon. I don't even know what the title of this talk is. Something with plants, I can tell you that. So let's pick up. Talked about Trypanosoma Cruzi. This is an American trypanosome. It is stercorarian transmission or stercorarian development. All right, so it matures to infectivity in the rectal gland of these rejuvid bugs, these kissing bugs. All right, kissing bugs deliver it, bite and crap method of transmission, and then they go into macrophages. That's going to be the first part. Get into macrophages, and then they have to transition to an amastogote form. And once you get an amastogote form, they're going to rupture, lyse the cell, which could be the cause of pathology, and then they'll go into other macrophages, so reticulotrophic strain, or they'll start infecting muscle cells. Because they're inside these cells, when they replicate, they're going to be in the cytoplasm replicating here. They're going to cause the cell to rupture. That's going to be a significant cause of pathology. All right, so we started with some of the pathology with the first stages, which would be a shagoma or Romagna sign. All right, and then we talked about what happens when it starts invading those muscle cells. They form pseudocysts. So these are the amastogotes that are replicating inside the cytoplasm. They keep increasing in number and enlarging the cell. It doesn't have a cell wall. That's why it's not called a cyst. It's a pseudocyst because it lacks any of those big walls. And then when it ruptures, it's going to lead to an inflammatory response, significant inflammatory response right in that location that could cause necrosis of nerve cells. Once you kill those nerve cells, you're going to stop causing those muscle cells to contract. And once they stop contracting, they're going to lose their function and their tone. So if you don't, as they say, if you don't use it, you lose it. And that has a lot to do with the muscles, right? If you're not using your muscles all the time, they will start to degenerate. And that's exactly what we see. And it leads to some of this gruesomeness. So if it's in the heart, you're going to kill some of those nerves that cause the heart to contract, and it leads to heart failure. All right. If it's in the GI tract, you get something called megaesophagus or megacolon, which is, again, you lose the function, but the food's still going through there. And what it's going to do is start to cause it to expand and stretch, leading to these very large intestinal tract, or a very large esophagus. Ready? All right, there's more to the pathology. There it is. There's my cursor. All right, so we do see difference in symptoms based on age of our individual. All right, so with kids less than 5 years of age, it's a bit uncommon to see some of these infections in the kids, but it can happen. And when they get it, you're going to see pseudocysts in almost any organ. So it's not just going to be restricted to muscles. They'll end up going and infecting other organs, liver, kidney, maybe bladder as well. But heart is going to be a dominant one, and it could result in 80% of the cardiac ganglia being destroyed. So those are the nerve cells of that heart. And usually, once you start doing that, death is going to be following. So symptoms in kids would be anemia, loss of strength. You get nervous disorders because you're disrupting nerve cell functioning. So you'll have lack of control, chills, muscle and bone pain. Again, inflammatory responses that happen, varying degrees of heart failure. Can progress pretty quickly. So in some of these kids, less than 5 years of age, death could result 3 to 4 weeks after the initial infection, which doesn't give you a whole lot of time. Doesn't give you a whole lot of time. Anemia, again, you're destroying cells. That's a pseudocyst. Your body's trying to repair them using proteins, using plasma. Just leads to decreased blood cell counts. Loss of strength, again, when cardiac ganglia are destroyed and your muscles start to deteriorate, then you'll notice a loss of strength. All right. Ready? The adults. You also get the same types of functions. Now you're getting your pseudocyst in the muscles itself. And where they go in the muscles lead to various types of symptoms. So this is where you'll see your central nervous system and the peripheral nervous system dysfunction. So you'll see some of the lack of the control of the muscles because the nerve fibers were damaged. That's part of our nerve ganglia destruction. Loss of heart muscle tone. Being tired easily. Right, your body not being able to keep up, megaesophagus, megacolon, sort of things, and we talked about that as what happens when those pseudocyst ruptures. About 70% of all cardiac arrests in young adults is due to this parasite, and it's due to those pseudocysts that rupture. And I mentioned we had a case, El Paso, that was a hot spot. You had unusually large number of 20 and 30-year-olds that were exhibiting cardiac arrest, heart failure, and dying. And on autopsy, you start saying, oh yeah, this was, it's unusual to see that. I'm going to say, it's possible that you can see it in individuals that are young, but it's uncommon. So to see the number that they did see, they started looking and said, oh yeah, a lot of these individuals had Trypanosoma Cruzi, which some of those individuals were in El Paso. So there was transmission that was happening more on the outskirts of the city, where you have more overlap with wildlife, but you also had migrant populations, individuals that had migrated there. A lot of them, they migrated as a kid. And now, 15 years later, 20 years later, you exhibit these symptoms. So this isn't necessarily a good parasite to have. And oftentimes, by the time you realize what you have, damage has been done. Damage has been done. Ready? Immune evasion. All right. So we're intracellular, and that sets up a difference with the African trypanosomes. So in the African trypanosomes, we're in the blood and tissue fluid. We are under constant assault of that host immune system. These guys are primarily intracellular. Yeah, they're going to be extracellular for a short amount of time. They're going to basically lyse the cell, rupture the cell, and then they're extracellular until they get into another cell. So because they're only out there for a short amount of time, they don't really have a need for the variant antigen types. If you don't have a need, why produce them? Why produce those VSGs? So how do they work around this immune evasion? They still have to deal with it. All right, well, what we see is that the cellular response is a primary host reaction, and it's very successful. All right, so your cellular response is basically your innate immune response, which you could say macrophages are the innate immune response, and they're using it. It's like, yeah, exactly, they are using it. But what the parasites have done is something more along the lines of modulating that host immune system. So it's going to do what it can to kind of reduce the cellular response, and it does so via interleukin-2, IL-2. So what does IL-2 do? IL-2 causes an increase in natural killer cells, cytotoxic T lymphocytes, and macrophages. Obviously, the parasite needs some of the macrophages, at least for the reticulotropic strain. But the cytotoxic T lymphocytes and the natural killer cells, those are going to be ones that are going to be effective at killing the parasite and clearing out the parasites. So the parasite doesn't really want these things around, so what they do is inhibit IL-2 production to reduce the amount of IL-2 that's being released, and they also downregulate the expression of the IL-2 receptors. It's an interesting pathway on how they do this. So macrophages can also send out, signals to increase IL-2. Parasites block that. They block the receptors. And by doing this, by inhibiting not only the production but downregulating the receptors, you're going to limit the effectiveness of IL-2 as a cell signaling molecule. So that's going to suppress, or what I like to say, slow down the cellular response. It doesn't stop it. You still get that cellular response, but it's at a much lower level, basically buying time for our parasite to reinfect macrophages or reinfect muscle cells. So it's not like a complete evasion like the African trypanosomes, but they do suppress the immune system to their benefit. Ready? All right, do we have it in Texas? Yeah, I've said we had it in Texas. This is kind of like a FYI. Yeah, I'm not going to say, do we have it in Texas? I mean, maybe I would, but not really. So yeah, Chagas disease is now a reportable disease in Texas. So if it gets diagnosed at a doctor's office, they have to report it to the state health department. So from 2013 to 2016, we've had 91 cases. 20 of them were individuals that were infected in Texas. And we've marked off areas where this has been found in dogs. So canines can serve as a reservoir hosts. That's kind of the idea, the thought that perhaps dogs are keeping Trypanosoma cruzi around in the bugs, which still makes it then a risk to the human population. Now, it's not going to be a massive risk because, again, this is over a 3-year time span. We've only had 91 cases. 20 of those were infected, or at least presumed or confirmed infected while living in Texas. Most states do not have to report Chagas disease, so it's a bit unknown what or how many cases we actually have in the U.S. Decent estimate is that we have 300,000 to over 1 million cases. Those are not 1 million cases that were transmitted in the United States. The vast majority of these will be individuals that have migrated from South and Central America. And vast majority of them, we're going to say 95%. You can estimate. So we have detected it here in Texas. We've detected it in the vector. We've detected it in vertebrate hosts. So in rodents and raccoons and small mammals. We've detected it there. But it's unknown if the strain that we're seeing, that we're calling T. cruzi in these animals and in the rejuvents, are actually the strain that can infect humans. So these are different species of Trypanosoma and Trypanosoma. They can all serve as a host. It seems a little unusual to have a parasite infect this range, especially a protozoan infect this range of different Trypanosomas. So it's a possibility that we have, let's say, a subspecies, or maybe they're not all Trypanosoma cruzi. Maybe they're some other species that cannot infect. So, yeah, we have it. We can find it. If you pick up Trypanosoma, bring it in. Ready? Let's move on to our next one, Leishmania. This is also a kinetoplast. Still, same group. Various species of Leishmania can cause the two main forms of Leishmaniasis. We have a cutaneous form and we have a visceral form. And the names kind of give you an idea on where the pathology is observed and where the replication occurs. So the cutaneous form of Leishmaniasis is where? Where do you think it is? Yeah, on the surface. So on the skin, lymphoid cells of the skin also infects macrophages and so forth. Cutaneous form affects 0.7 to 1.2 million people per year. The visceral form affects fewer people, but still it's 0.2 to 0.4 million per year, so 200 to 400,000 per year. Here's our distribution of cutaneous forms. Kala Azar is our visceral form. So Kala Azar is more, you're dealing with Africa, Middle East. Cutaneous form, we see it in South America, we see it Africa, we see it Middle East, and so forth. So you're going to see it. Cutaneous form is the more widespread, more common one. For all of the species of Leishmaniasis, transmission occurs when they are injected by the host, so that they're going to be in the salivary gland and they get injected, or they're going to be regurgitated. And I think the life cycle that we go over, this is the regurgitation. So they're going to replicate in basically the foregut, fore and midgut, and then when the insect takes a bite, they're going to vomit a little into the human, and when they vomit, they're going to deliver the infective stage. So, note here, salivarian and stercorarian does not apply. Why do they not apply? These terms only apply to the African trypanosomes and the American trypanosomes. That's it. So the only two type groups that include these types of transmission. All right. Ready? All right, life cycle. And we'll put this back up. So I put on the slide like some of the key points of the life cycle, and we'll have them on there. We'll try it. I did not like this chalk last time. Open it up. I believe I gave you a full page to do the life cycle. And you'll see why. Just erase these. All right, so we'll cover all of them. We'll start here with our metacyclic form. This is a metacyclic promastigo, which incidentally is the form that we could see on the slides in the lab. So that was from a tissue culture, a nutrient culture, to try to replicate what they'll encounter in the humans, but it doesn't. It replicates more like it's in the insect. So you see these promastigo forms. All right. So it's going to get regurgitated. Into our host. All right. So now we have our promastigo. And it's going to be in our tissue fluid. Blood and tissue fluid, you could say. All right. And this will be phagocytized by macrophages or lymphoid cells of the skin, which are a group of immune cells. All right. So we will have our promastogote. It will be in a parasitophorous vacuole. Of our macrophages. Or lymphoid cells of the skin. So there's our cutaneous portion of it. Which one it goes into kind of depends on the species. Macrophages, they normally go into macrophages. That allows them to spread. Some of them stick just to the lymphoid cells. All right. Then, once we get into here, we will transform into an amastogote, which at the time, these were called Leishmania Dhanavani bodies, because Donovan and Leishman both came out to identify this stage as causative agent to Leishmaniasis. So Leishmania was named after Leishman, and then since that point, we've discovered that they're similar to the other kinetoplasts, and we call them amastogotes and so forth. But they're going to transform to the amastogote. They're still in that parasitophorous vacuole or of the macrophages. You're going to have replication. It's ridiculous. And cell lysis. Cell lysis, and then reinfect. Reinfect additional cells. So macrophages, lymphoid cells of the skin. Some of them will be in the tissue fluid. This is ridiculous. I can't use that piece. I don't have much. Blood and tissue fluid. Blood and tissue fluid that can now be picked up during blood meal. All right. Whoops. So let's do that. So we're going to do human, but several mammals serve as reservoir hosts. Our insect host are sandflies. Yep. Blood meal. That's going to be our sandflies. Take a blood meal. Pick up the amastogotes. All right. We will now have our amastogotes. That will go to the mid or hindgut. Depends on the species. All right. At which point they will attach and then transform into procyclic promastogotes. We are still attached mid or hind gut. All right. Procyclic form. Replicates by binary fission. replicates by binary fission. Some of them will detach and migrate. All right. Detach and migrate, where the promastogote goes to the esophagus and pharynx. And once they get there, they will now attach. Attach to the epithelial cells. Here, they will replicate again. It will replicate again. And this is where I think it gets interesting. You will have some of these detach. Some of them will detach. Where we have our metacyclic promastogotes in the foregut. So we're already in the foregut with the esophagus and pharynx, but we've detached, and we're there. All right? But these guys can also detach and attach to the cells of the stomodial valve, where they become a haptomonad parasite sphere. It's attached to the lining of the stomodial valve. This stomodial valve in the foregut regulates food, regulates the movement of food from the foregut to the midgut. All right? These guys, these haptomonad spheres, they're promastogotes, but they look spherical. All right? They line this, and what do you think it's doing? They're here. It's a valve. You're going to start getting blockage. What happens when you start getting blockage? What does the insect want to do? Regurgitate. Exactly. So it's thought that these guys are helping with that regurgitation process so that the insect can get more food. But it doesn't end there, because we haven't talked about like what's triggering this. So here's the thing. We have our metacyclic promastogotes in the foregut. All right, they're not replicating, but we know some of these will transform and reattach. Transform and reattach into promastogotes that will replicate again, and some of those will now, again, detach to produce these metacyclic forms. They also secrete a substance called PSG. And this PSG is going to stimulate the attachment and the transformation of some of these guys into the heptamonad parasite sphere. What triggers this? What triggers all of this stuff? So some of this will already occur, but it doesn't occur at large numbers. This PSG stimulates it, gets a lot of them in there to increase the blockage of this valve that then stimulates the regurgitation. This step here, transform and reattach the promastogotes that then secrete the PSGs, this is all stimulated by blood and plasma. It's stimulated by mammalian blood and plasma. So here you have this situation where the sandfly is taking a blood meal. The first blood meal, after it gets attacked, after it's infected, is going to further stimulate the production of all these heptamonad spheres that are going to cause a blockage. So then the next time the sandfly bites, it's going to start transmitting this parasite in many more numbers. Totally far out there. And I will tell you, I did not learn that. I did not learn this in my parasitology class. This is newer stuff. Where it's like, I would have just learned, yeah, we're in the amastigo. We're in the mid to hind gut for the procyclic promastigo, and then they detach and they're metacyclic up in the esophagus. And we knew they were regurgitating. We knew that. But how they did that, how they regurgitated, or even why, wasn't understood. And then all of a sudden you start seeing all these different pathways that are happening. They asked me, that's crazy. Questions?
Do they transform from when they go from a metacyclic promastigote to a promastigote? So they're just transforming.
They're transforming back to like a procyclic form. And they're different. These are different. So they notice that those are two different things. They can distinguish between those. These secrete that PSG compound that will further stimulate these heptamonad spheres. These do not. Those do not. Pretty far out that they could even figure that thing out. So that PSG is promastigote secretory gel. Great, I mean, that's an absolute great name for it. Very clear. Very clear as to what it does. So let's leave this up. 2 morphs in the life cycle, that's it. We'll go back and talk about this, but we have our promastigote and our amastigote. That's all that we find in Leishmania. African trips, it was trypamastigotes and epimastigotes. The American trip, so Trypanosoma Cruzi, has the 4 that I asked you to know. Trypamastigotes, epimastigotes, promastigotes, amastigotes. All right, so we have 2 morphs in the life cycles. We've got our amastigotes and promastigotes. Those are the Leishmania Dhanavani bodies. Sandflies are going to take a blood meal about every 5 to 6 days. Every time they do that, you're going to cause some of these metacyclic promastigotes to reattach and transform back to a replicating stage. Right? Purpose of that, you're going to increase the number of metacyclics you have. You're just further increasing the chance that we're going to transmit, but it's also going to increase the number of heptamonad parasite spheres. Right? They attach, destroy that valve. Right? And this PSG helps to obstruct as well. Promastigote secretory gel, PSG. Again, you plug up the esophagus, and then they're going to have to vomit. And so you get some descriptions of like where it is. So, proboscis of your sandflies, stomadeal valve, helps regulate the food. Here in the metacyclics up here. Once you start blocking it, insects are going to try to vomit it to get rid of that plug. And half the monad spheres help to kind of increase that plug formation. Totally different. Ready? Promastio secretory gel. It's pretty crazy how they found that stuff out. And as the diagram shows, the arrow, step 1, vomit. Step 2, take your blood meal. Clever, clever, clever. Ready? Moving on. All right, we're going to start with immune evasion. So we're inside the cells. Right, so you don't really need your VSGs and VATs. Right. We're living inside the cells that should be clearing out the parasite, much like Trypanosoma Cruzi, right, infecting macrophages or lymphoid cells. So what's their immune evasion mechanism? Well, their immune evasion mechanism is basically their surface coat. They're going to change their surface coat, not as like a VAT type, but it's going to change the thickness and what's there. So the observations that we see is that the procyclic promastiote has a surface coat, like a glycocalyx, of about 7 nanometers. When they transition to the metacyclic form, it's more than 17 nanometers. So more than doubles its size. And then the amastogote, you really can't see this glycocalyx that's out there, that surface coat. All right, and it's so just seeing these changes, seeing the differences in thickness of these different life cycle stages suggests that there's something going on, something happening with these proteins, and they're associated with immune evasion. So the amastogotes are almost absent, which is like, okay, well, these guys must not be a major target. So but you get the increase in these molecules in preparation for getting into the host. So what's their function? So we've got a couple that we're going to talk about. Ready? A couple that we're going to talk about, they've got some long names, but we can just kind of know the abbreviations. That should be sufficient. All right, so our promastigotes have LPG and GIPL. So LPG is a lipophospholipid. GIPL is glycosyl inositol phospholipid. All right, so LPG and GPL, those are going to be our two surface coat molecules. LPG is continuously shed. All right, it's going to be constantly shed, but it's going to change as we switch life cycle stages. All right, its function is twofold. One, it's going to inhibit complement-driven lysis. So complement-driven lysis is effective at killing off these parasites. But the parasites, once they get inside the host, they have to find their way inside a lymphoid cell or a macrophage. So before that time, they're getting nailed by complement-driven lysis. They inhibit it. And LPG does that. So they're going to try to stop complement-driven lysis until they get inside that macrophage. And then once you get inside those macrophages, they have to prolong or delay fusion of phagosome with lysosomes. They have to delay it long enough so that they can transition to our amascote stage. So LPG is responsible for both of these items. They inhibit complement-driven lysis. They inhibit phagosome-lysosome fusion. All aimed at kind of just slowing things down so that they can transform. They can infect and then transform to an amascote. The other one that's on there is GIPL. GIPL, glycosyl Lipid. It is not shed. It is on there. It's going to remain on there until life cycle changes. This is the most abundant surface molecule. It's 10 times more abundant than LPG. However, it's small and it's close to the surface. It's there. We think it has a protective role, but we don't really know what it is. We don't really know what it is. So GIPL probably has some role. And that's if we kind of went back here, LPG, GIPL, GPI, pre-GPI. You got your anchors, small ones. To kind of give you an idea of what they look like. All right, the amastigotes, they are not susceptible to the acidic cleavage. So to your proteases and stuff that would typically occur inside that phagosome lysosome. All right, so they don't have to worry about it. They don't have to worry about delaying anything. They just get in there. It's like, yeah, throw what you have at me. I don't care. So because of that, you don't need LPG and you don't need GIPL. So those are down-regulated in your amascote stages. But they do inhibit reactive oxygen intermediates. What are those? Give me an example of those. Reactive oxygen intermediates. Yeah, the peroxides. Yeah, that's part of our immune system. We can utilize these. These are kind of like, again, we've seen so many different foreign invaders that our immune systems developed, come up with ways to eliminate them. Antibodies don't always work. Cellular responses don't always work. That's why you've got your complement-driven lysis. That's why you have these reactive oxygen species out there. So amascotes can get cleared out by them. We'll get damaged by them, so they try to inhibit the production and try to inhibit their actual action on them. So we do know that, and that would be a type of immune suppression. So the amascotes, they don't need LPG or GIPL, but they are inhibiting that reactive oxygen species. Ready? Amastigotes. So a lot of this is that promastigote. Get into that macrophage, transition to the amastigote, and then you're doing pretty good. All right, we've got 3 species of Leishmania to talk about. They all have similar life cycle, and we could have broken it apart and said, okay, this one's in the hindgut, this one's in the midgut, and so forth. We're not going to do that. We're just going to have one life cycle pattern for Leishmania. All right, but these different species lead to different pathologies, different symptoms, and different common disease names. All right, so Leishmania tropica is West and Central Africa through the Middle East and Asia Minor to India. All right, tropical, think tropical, equator, equatorial region. This parasite is responsible for, at least partially responsible for cutaneous leishmaniasis. It has been called oriental sore. It's been called Jericho's boil. All right, so you go back to history. This was all being tied back to Leishmania tropica. And what does that mean? What's an oriental sore? What's a Jericho's boil? It's this. It's almost like an open wound on the skin. It's a skin lesion. That is 100% what it is. This is due to the parasite infecting those lymphoid cells of the skin and causing them to rupture because they're replicating and lysing them. Now, our parasite on all of these, they're going to be on the edges. This part, they've already been damaged. They're having a hard time healing. But your parasites are damaging and rupturing more and more of these lymphoid cells, causing this lesion to form. It's an open wound, basically. This will heal with a scar. Heals with a scar. And when you have it, you then tend to gain some protective immunity against future infections. So if left untreated, yeah, it'll resolve itself. Might take some time. So Leishmania tropica, oriental sore, Jericho's boil. That's cutaneous leishmaniasis. Ready for the next one? Leishmania Dhanavani. This is India, China, Bangladesh. Southern Asia. This is predominantly leads to visceral leishmaniasis. The visceral leishmaniasis has been called Kala Azar and dum-dum fever. Okay. You've heard of dum-dum before, right? Where have you heard it? See, both the sucker and the movie, right? What is it? Dum-dum like gum-gum? Night at the museum. Right, it's an actual place, location. So what is this? Visceral leishmaniasis, you have the Leishmania parasite going into the spleen, liver, mesenteries, lymph nodes, intestines. So it goes internal. You're not going to have those open wounds, those skin lesions. Because you're in there, you're still causing damage, you're still causing disruption, lysis of macrophages and so forth, leading to progressive wasting. You can have anemia, and you can also have hepatosplenomegaly. So enlargement of the spleen, enlargement of the liver, and this is an individual, a young child. This is their spleen, which is drastically enlarged. It's not supposed to be that large, and they've also marked off the liver on that individual as well, so massive enlargement. This will kill if it's left untreated. We do treat them. We do treat individuals. But what can also happen is that it can resolve itself. And so you get some wasting, and then all of a sudden you come back, and then it reappears as post-Kala-Azar dermal leishmanoid. And what happens is it's instead of staying inside the body in visceral form, it goes back to the skin, but it's not going to start infecting those lymphoid cells and causing the lesions. Instead, it produces these red, depigmented nodules, most prominent on faces, that can enlarge to get really some gruesome disfigurement. So we say it can develop following inadequate treatment. You treat them with drugs, but you didn't fully clear off the parasite. Some of it was there, so then it could come back. So you can notice Kala-Azar is the visceral leishmaniasis. It's not completely treated all the way. It comes back as this post-Kala-Azar dermal leishmanoid. This is Leishmania Dhanavani. All right, we'll stop here, and on Friday, we'll talk about Leishmania brasiliensis, New World. And there's also Leishmania, I think Mexicanus, but that's probably it's pretty also a pretty gruesome one.